The Brexit financial settlement or divorce bill is a sum of money due from the UK as it leaves the EU. The bill is a complex calculation comprising of various liabilities and entitlements to a portion of EU assets. There is debate over the size and duration of the continued support for various EU schemes, such as an exact net amount owed is unknown, hence there is an opportunity for bargaining. It's an integral part of the withdrawal settlement, so reneging on it would mean leaving the EU with no transitional arrangements. If negotiations broke down, the EU are likely to seek redress to the International Court of Justice. Assume the bargaining process to be initiated by the UK, proposing an initial bill. The EU can then choose to accept this or counter. This bargaining process continues. There is a finite number of rounds, as negotiations must be completed within guidelines set by Article 50. If no offer is accepted by the final round, then a financial settlement will be arranged by courts. Assume each player to be impatient, as both are eager to arrange a settlement. A zero-sum alternating offers game is described thus far. For example, if the bill is 50 billion, one player will receive this as a positive payoff and the other as a negative of this. The complex solutions to these strictly competitive games by computer algorithms is beyond the scope of this analysis. Also, negative payoffs would be discounted to less negative values when assuming the discount factor less than 1, which cannot hold given impatience. So, inspired by Rubinstein, view the divorce bill as a pie of unit size 1. Both players propose distributions between them, with both players' utility increasing in the fraction of the pie they receive, implying for the UK that a greater fraction they receive results in a lower bill, whereas for the EU a greater fraction implies a greater. The discount factor between 0 and 1 provides a way of evaluating future payoffs. A low discount factor means the player is impatient and discounts future amounts heavily. They reflect an overall level of impatience for each player, determined by various qualitative factors, as we assume the bill to be interest rate adjusted. A few reasons why the UK may have a lower discount factor are listed. Here is a formal display of the game. Both players are assumed to be utility maximising rational agents. Player 1 is UK and player 2 is EU, and the set of real outcomes is bounded by the sum of their payoffs equaling 1. The subscript and superscript denotes the player and round respectively. The player's utility is an increasing function of both their payoff and their discount factor, and a decreasing function in time, as the discount factor is less than 1. Call player 1's discount value mu and player 2's epsilon. If no agreement is made after t-1 periods, then an exogenous disagreement payoff is enforced in period t by court. For finite t, we can find the subgame perfect equilibria by backwards induction. Supposing t equals 3, in period 2, the UK can obtain his disagreement payoff in the next period by rejecting player 2's present offer. Hence, the UK will reject the offer if the EU's proposal for the UK is strictly less than the discounted value of the disagreement payoff. Based on this, the EU can obtain at least 1 minus this. In period 1, the EU knows that he can obtain this in the next period. Hence, he will accept the present offer if the payoff proposed to him is at least his discount factor multiplied by what he could achieve in the next. So, in the Pareto-efficient subgame perfect equilibria, player 1 makes the offer shown in red and player 2 accepts in period 1. Supposing instead that t equals 5, the subgame perfect equilibria for this scenario can be solved by equating it to the case in which t equals 3, but instead of the breakdown payoff being as before, it is now the equilibrium found in the case where t equals 3. By backwards induction, the equilibrium payoffs are shown. The analysis can further be extended to a general equilibrium payoff for odd-numbered rounds. Each player's payoff is an increasing function of his discount factor and decreasing in the other players. Payoffs increase with respect to their disagreement payoffs. Player 2's payoff tends to 0 as n becomes large. All else equal, there is a first mover advantage. Here is a graphical representation of the game for t equals 3. The dotted line represents any amount between 1 and 0 to the other player that can be offered. Notice how the pie is discounted at each stage of bargaining. There is a number of perhaps unrealistic assumptions in order for the equilibria to be met in the first round. Firstly, the theoretical number of rounds must be common knowledge. In practice, this is unlikely to be true. For example, the initial deal was rejected in Parliament, hence further rounds of bargaining. The disagreement payoff is also unbeknown to each player before bargaining, and is only decided if no deal. So this may be the resulting equilibrium depending on each player's belief about disagreement payoffs. The discount factors are also unknown. The game is also assumed to be a two-player game between those negotiating for the UK and the EU. In reality, there are more players involved in the decision-making who must be appeased, resulting in a number of red lines for both players which must be incorporated into the Realistic lessons learned from the simplified model of negotiations include that players should signal to suggest that they are patient. A few ways in which they can do this are shown. The only Pareto-efficient outcome is the equilibrium described, as the pie is not discounted here. The UK should try to propose an offer that will make the EU accept in the first round. Players should attempt to estimate the other players' discount factors. A less realistic lesson is that the UK should try to have the first offer, as power comes from the ability to propose, and that the UK should try to raise the expectation of their disagreement